The liquid drop model. You know, in order to describe the nucleus in general, we don't have one theoretical model. We have many models, each one describe some properties, or many models can describe one properties. Okay, it's very important, this point. So first of all, to describe and understand the masses and binding energy of nuclei, we use the liquid drop model. It's called the liquid drop model because nuclei are assumed to behave in similar way to a liquid. Okay, I don't want to write all the properties or all the similarity between the liquid drop and the nuclei, but you have a lot of common properties. For example, you have the shape, circular shape, the interaction between the molecules in the liquid drop, and the nucleon interaction. You have, and the scattering between the molecules. You have many properties, many similarity. For this reason, we can use the liquid drop as a perfect model to describe, to understand the binding energy. You know, we calculated the value of the binding energy, which is equal to the energy of the nucleons minus the energy of nucleus. Okay, we can calculate the mass of the nucleus. Okay, we have Mn, mass of the nucleus, of the energy of the nucleus, which is equal to, we can put this one here, so is equal to Zmp times c square plus n, you know n equals to a minus z, equals to a minus z mn times c square, plus or minus the binding energy. You put it here. Okay, finally we find this relation. You know, by this expression we can find the value of the binding energy. It's easy. But by applying the liquid drop model, we find a new expression of binding energy. This energy, or this binding energy, depends on many factors. Some factors help or contribute to increase the binding energy, and we have some other factors can reduce this this binding energy. Okay, for example, the first term is a volume term, the second one is a surface term, the third one is a Coulomb term, we have asymmetric term, and we have pairing term. I want to talk about each one in details. First of all, we have the volume term. In general, physically, the nucleons inside the nucleus, I don't talk about the nucleons at the surface of the nucleus, just about the nucleons inside the nucleus. Each nucleon is bounded with another nucleons in all sides. Okay, for example, this one is bounded to this one, this one, this one, this one, and this one. Okay, and if you take another one, also is bounded with many neighbors in all the sides, in all sides. But I told you I don't talk about the nucleons on the surface, okay, because they are bounded only from one side. Here we have nothing. This term, the volume term, contribute to increase the binding energy because in this case, the strong nuclear force is very bounded, is very strong, very tighty. So here we have a positive value of B volume equals to AV times A. Here I don't need to talk or to demonstrate this expression. Okay, AV is a constant term. Experimentally, we have its value equals to 15.85 mega electron volt. A is a mass number. Why B volume depends on is a function of A, only A, because in general the volume of a spherical object equals to 4 divided by 3 pi r cube. We put r equals to r0 a1 over 3. We get here 4 divided by 3 pi r0 cube times a, only a. Okay, so the volume in general depends to the is directly proportional to the mass number A. Okay, we go to the second. The second term is the surface term. You know, all the nucleons at the surface of the nucleus are bounded by only one side. Okay, we don't have external relation with the neighbors. So in this case, this term will decrease the global value of binding energy. Okay, we have a very bounded system. If we have one nucleon, is bounded from all the sides, but this one it's not from all the sides. We have only one side. In this case, we must put minus because it decreases the global value of binding energy, equals to AS times A power 2 divided by 3. Why? It's in function of A power 2 over 3 because the surface of the spherical object equals to 4 pi r square. We put r here. We get finally 4 pi r0 square times a power 2 divided by 3. So b, this term must be in function of a power 2 divided by 3. Empirically, by experiment, we find the value of AS, which is equal to 18.34 mega electron volt. Okay, let's go to the third term. This term later I need to prove and to find the expression of B Coulomb. Okay, we have to find this expression. You know, between the positive charge we have a repulsive electric force. So this repulsive force will push away the protons. So this term will contribute to decrease the global binding energy. So we have minus. Okay, B Coulomb equals to minus AC times Z factor Z minus 1 divided by A power 1 divided by 3. We will calculate it later. Empirically, we calculated A Coulomb, which is equal to 0.71 MeV. Okay. the symmetric term or asymmetric term. You know, when we talked about the neutron number in function of the atomic number, you know, all the stable nuclei have more n number than z. The number n is slightly bigger than z. So we don't have a symmetric number of n and z. Okay? Only in the case of a lighter nuclei here, in this case, we have the same number of n and z. But here, we don't have this symmetric. So here, we must take this term into account. B asymmetric equals to minus AA times n minus z squared divided by A. This asymmetry can contribute to reduce the global value of binding energy. Okay, for this reason we have minus. AA is the asymmetric term, empirically equals to 23.21 mega electron volt, and B asymmetric is inversely proportional to A. I don't want to go in details about this term, just you have to know the general expression of B asymmetric. We go to the last one, the pairing term. You know, it's important to know how many nuclei with an even or odd number of protons and neutrons, because at this point you have to know how many nuclei are stable and how many nuclei are not stable. We found that in the case of even Zn, we have the most number of stable nuclei. If we have about 177 nuclei stable. In the case of Z even and N odd, for example, we have 10 Z and not 10, we have 100 Z and we have 101 N. In this case, we have 58 number of stable nuclei. In the case of odd Z N even, we have 54. In the case of N odd and Z odd, we have only 10. So it's important to have an idea about this pairing term, because each time this quantity of stable nuclei will change. Okay, so in the case of even nuclei, we have a strong binding energy. So in this case, this term will contribute to increase the binding energy. In the case of odd, for example, in this case, the pairing term will decrease the global binding energy. So here we have to calculate the situation and to find the pairing term. The value of B pair, okay, equals to positive. It has a positive value in the case of even nuclei, because the number of stabilities of the stable nuclei is big. In this case, we contribute to increase the binding energy. In the case of even odd or odd even equals to 0, because the number of the contribution to the stability and instability will be the same. So we don't have any effect of the pairing term. In the case of odd, the term will be negative, because this term will decrease the binding energy. In general, the value of B, the value of this symbol equals to AP times A power minus half. So we can say delta equals to AP times 1 divided 1 over half. So B pair is inversely proportional to A half. Okay, empirically AP equals to 12 mega electron volt. That's all about all the factors which can affect the values of the binding energy. And here to calculate the expression of the global expression of binding energy by using the liquid drop model, we have to add all the terms. Okay, the volume, surface, coulomb, asymmetric, and pairing. Okay, this one, this one, this one, this one, and this one. You know, this term can be written like this, or minus AC Z Z minus 1 divided by A power 1 minus 1 over 3. We talk about the Coulomb term later, okay? Because we have to do some calculation. And you see here, we have the value of pairing term, and we have each value here. We can add them, and we can calculate them. We will have some application later. Here, let me calculate the average energy, binding energy per nucleus. We can say here per nucleon, okay? Average binding energy, we can say here binding energy per nucleons. Per nucleon. I mean, what is the value of the binding energy to extract one nucleon by using the liquid drop model? Because this value is calculated before, but now we have to use the new relation of the binding energy. Okay, I will write the expression directly here. You know, we have this one here. To calculate the binding energy per nucleon, we have to divide the total binding energy divided by A. This one divided by A here times A times A. This one, we have A and A. We get here AV minus A surface. We have A power 2 over 3 times A power minus 1, okay, minus A coulomb Z square divided by A times A 1 over 3 equals to A 1 over 3 plus 1, okay, minus A symmetric N minus Z square divided by A square plus delta pairing term Z N divided by A. Okay, we calculate this one. We add 2 over 3. We subtract minus 1. Finally, we get the final relation will be here. We have AV minus A surface. This one minus this one, we have minus 1 over 3 minus AC 1 over 3 plus 1 equals to 4 over 3 Z square minus asymmetric. We have A square here, okay, and minus Z, it's okay, plus delta divided by A. This is the general expression of the binding energy per nucleon. Okay, let me here draw the binding energy per nucleon in terms uh, of the nucleon, of the mass number A. Okay, of the mass number A. In general, if we take only the volume term, only this one, we find that the binding energy per unit mass number A per unit per nucleon is constant for all the nuclei. Okay, I mean I take into account only this one. We don't take this. And so on. If I take the volume plus surface factors into account, only these two terms, we get this relation. If we take and so on, we arrive to the volume, surface, Coulomb, symmetric terms. We get this relation. Finally, we must have a similar relation like the last one, like this one. We come back to this one.